In this video, a comparison is made between a classical and an AI controller based on a neural network. The task is a classic control engineering task, the inverse pendulum. It is examined which of both controllers solves this control task faster. Which solution is optimal? What problems are there? This video tries to find out. Have fun with it. The Gymnasium and Gym software is used for this purpose. The license can be found on the cover sheet. Thanks to the creators of the Gym and Gymnasium library for this excellent software to get an easy introduction to artificial intelligence. This is the cart pole without controller. Drops down immediately. The short period of time results from the termination criterion being reached. This is the cart pole model with a PID controller. The pole angle and pole angle velocity are controlled, so that the pole remains in its initial position. The uncontrolled drift to the right side is problematic. This is the cart pole with the optimized PID controller. In addition, the position of the cart is integrated into the solution of the control task. This solves the problem of lateral drift of the cart. A stable position is achieved in approximately 1 second. Now we want to watch a controller based on a neural network, which learns an optimal solution on its own. Here, the neural network is taught via reinforcement learning. Rewards lead to the neural network learning to keep the pole in the vertical position. The lateral deviation of the cart is not included in the reward mechanism. The goal is to hold the pole in a vertical position for 500 steps. Many attempts are necessary to achieve this goal. After 10 minutes, the teach-in of the neuronal network is already considerably advanced. You can see this by the fact that the number of steps allowed in an episode has increased considerably compared to the first learning episodes. After approximate 23 minutes, the trained result continues to improve. For the first time, 500 steps are reached in which the pole is in a vertical position. However, due to the learned behavior, the cart tends to always move to the left side. After approximately 75 minutes, a convergence of the learning process can be seen. With exceptions, it is possible to keep the pole in the vertical position. This ends the training mode. About 75 minutes were needed for the independent training using reinforcement learning. Now we want to test our trained neural network. Can we use the model to keep the cart pole in an upright position for a longer period of time? What abnormalities can be observed? We observe 3 points in time. First point is start of test mode, second point is after 15 minutes, and the last point is after more than an hour. Successful teach-in can be seen immediately at the start. The pole remains in a vertical position. There are no aborts. This can be monitored using the timer. The same behavior after approximate 15 minutes. However, it can be observed that the cart pole tends to move towards the left side but not or only very slightly to the right. The reason for this is that the cart pole often were made movements to the left and less to the right side in training mode. After more than an hour, a conclusion can be drawn. The cart pole can successfully master the task assigned to it with a neural network value. The cart pole is juggled for over an hour in such a way that it remains in a vertical position the entire time. And all this was achieved by successfully learning from data, and no functional algorithm is necessary as with a classic controller. This is already a remarkable result of artificial intelligence. What should be summarized? The classic control task cart pole can be successfully implemented with both methods, PID controller or neural network. In the current implementation, the classical PID controller is superior to the neural network in terms of the functional accuracy achieved. In principle, it can be said that with the algorithmic solution of the PID controller, it is easier to determine which screw to turn if an optimization is to be made in a certain direction in relation to the task set. With the functional algorithm, it is quicker to see whether the desired optimization occurs than with the neural network. With the neural network, a time-consuming learning process is required each time to see the desired improvements. It must be evaluated whether an optimization of a data-driven neural network can be carried out via an adapted reward in reinforcement learning or whether restriction of the degrees of freedom in the training process will bring further progress. This video was created using Microsoft Clipchamp software.